recall our last few lectures, we have been discussing about the various sequential circuit components which helps us in designing synchronous sequential circuits. In particular, we had discussed the design of the various kinds of flip flops, how they can be excited, how the flip flop states can be changed from the various input states to the output states, and of course, we have seen the different ways in which we can convert one kind of flip flop to another. So, now with that background, let us see how we can design or synthesize general synchronous sequential circuits starting from the specification. Our target is to obtain the final gate level and the flip flop level circuit from the specification. So, the title of our talk today is Synthesis of Synchronous Sequential Circuits. We are starting with part 1. Okay. So, we have already mentioned earlier that circuits are of two types, combinational and sequential. So, let me repeat it once more, because this difference is extremely important. Now, what I had said, a combinational circuit is one where whatever inputs you are applying, the outputs will be depending just on those applied inputs and nothing else. Okay. But in contrast, when you have a sequential circuit, here you are applying some inputs, all right, but the outputs that are generated, that are dependent not only on the inputs, but also some internal history of the system. There is a concept of a history which is maintained by the system, which is called the state of the system. So, whatever the output you will be getting, that will be depending not only on the inputs you are applying, but also on which state the circuit is presently in. So, we mentioned very briefly earlier that the flip flops that we have studied, they help in maintaining or remembering the state of such a sequential circuit or a sequential machine we sometimes call. Okay. So, whatever we have said is mentioned here. In a combinational circuit, the outputs depend only on the applied inputs, but in a sequential circuit, the outputs depends on the applied inputs and also on the internal state. This is what I just mentioned. And another point to note is that as we go on applying inputs in some sequence, the circuit also goes on changing its state. So, the state of the circuit or the state of the system changes with time in response to the applied inputs. So, this is an important point. The internal states of the machine or the circuit changes with time. And just one thing to remember, I am saying that the system or the circuit is remembering some history, okay? That is the state of the system. Now, from a practical point of view, you just think, if the number of possible states in a system is infinite, can you really build such a system? You see, the state or the information about the state you maintain in flip flops or a set of flip flops. If you have n number of flip flops, they can be in 2 to the power n possible combinations. So, a maximum of 2 to the power n distinct states can be represented. But if we talk about infinite states, this indirectly means that we require an infinite number of flip flops, which practically you really cannot build, right. So, from practical point of view, we talk about something called finite state machines, or in short FSM. Finite state machine is nothing but a sequential circuit where the number of states or the internal history information is finite in number. That is why it is called finite state machine. Okay. And of course, we mentioned this repeatedly, that most of the practical circuits we see around us are sequential in nature. Very rarely you will find a circuit where the output depends only on the inputs and not on the history. Okay? All right. So, let us look into these finite state machines in a slightly more detail. The first thing is that whenever we talk about a finite state machine or a sequential circuit, well, we have to start from somewhere, right. Somehow we have to specify the behavior of the circuit. For example, in a combinational circuit or a combinational function, we specify the behavior either by using a switching expression, a function, or by using a truth table and so on. So, in exactly the same way, for a sequential circuit there must be some very systematic way to specify the behavior of the circuit or the system. Okay. So, the two ways you can do that is either in the form of something called a state table or a state transition diagram. You note that state table and state transition diagram are equivalent. They represent the same information, but in two different ways. State table is a tabular representation, state transition diagram is a diagrammatic representation. So, it is fairly straightforward to convert from one form to the other. So, when you are actually designing a sequential circuit, it is good enough to start with any one of the two, you do not need both. But in the examples that we shall see in some subsequent lectures, we shall be showing you both the representations just for your convenience, right. Okay. There are some other ways also to represent finite state machines, particularly more complex ones. Like one of them is algorithmic state machine or ASM. This we shall be discussing briefly later. Okay. But right now, we shall not be considering this ASM chart in this discussion. We shall be talking about the state tables and state transition diagrams. Okay. Let us take a very simple example to illustrate. Consider that we want to build a circuit. This circuit would be like this. There is a circuit which will be having a single input, let us say x. It will be having an output z, and of course, there will be a clock. So, what you are saying is that in this input x, we are applying a sequence of bits, that means a serial bit stream. For example, we are applying a bit stream like let us say 0 1 1 0 1 1 1 1 0 1 0 1 1 1 and so on. Now, the circuit should be such that you will be detecting 3 or more consecutive ones in this stream, and these bits are applied in synchronism with the clock. We apply a bit, apply a clock, apply the next bit, apply a clock and so on. So, the output will become 1 whenever it will detect 3 consecutive ones, 3 or more in fact. So, in this case the output will be all through 0, it is out here it will become 1 because there are 3 ones, there are 4 1, here also it will remain 1, well again it will become 0 and again it will become 1 out here because there is again 3 ones. So, we want to design a circuit like this, right. So, the first thing that you realize is that well, this is not a very trivial or very simple kind of a specification. Somehow, we have to represent or capture this information in the form of a table or as I said in the form of a diagram, state transition diagram. Let us see how from this specification that we want to detect consecutive sequence of 3 or more ones, how we can formally capture the behavior and represent it in a systematic way. Okay. Let us look into the diagram on the right, this diagram first. You see here I have shown a diagram This is called a graph, where I have some nodes or vertices which are represented as circles. Here you see there are 4 such vertices A, B, C, D. These vertices represents states of the system. So, there are 4 states. Now, how many states will be there for a given problem, that you will have to figure out. The designer has to figure out how many states are required. In this problem, as you will see, 4 states are sufficient. Okay? These are A, B, C, D, and I am saying that state A is the starting state. So, when you start the system, it begins with state A. There can be a reset input. So, whenever you reset the system, it will initialize itself into state A. Now, what I am saying is that whenever there are consecutive 3 1s, the output has to be 1. So, how do you capture this in this diagram? Well, we shall be discussing this in more detail later, but let us try to explain with this example how we have constructed this diagram. Well, while in state A, see there are some arrows you can see, these are edges. These arrows connect one state to another, and these arrows are labeled with 2 numbers, let us say alpha and beta. This alpha indicates inputs, that means what input is coming, and beta indicates that what output will be generated. You see, when you are in state A, you are looking for 1 1 1, right, but if you see there is a 0, well, you will have to remain in state A, because you have not yet started the sequence. It is a 0. So, you have no information about 1 1 1, you remain in A and your output is 0, because you have not yet got 1 1 1. But as soon as you get the first one, let us see this edge, you get the first one, you go to state B. State B indicates that I have found a single 1 has been found, that is the meaning of state B. Okay? And still the output is 0, because we have found only a single 1. Now, while in state B, that means you have got a 1, if you find there is again a 0, that means again you have to start from the beginning. So, if you in state B, if you see that the next bit is 0, you again go back to state A, right. But if you find that there is another 1, which means now I have seen 2 1s, 1 1, I go to state C. So, state C indicates that I have seen 2 1s. Similarly, while in state C, if there is another 0 coming, you go back to state A, you have to search from the beginning again. But while in state C, if you get another 1, which means, let me clear this, which means 1, 1 and 1, then you go to state D with the output of 1, because now you have found 3 consecutive 1s, B, C and D. D means at least 3 consecutive 1s have been found, and here you see the output is also becoming 1. Now, while you are in state D, which means already 3 1s are there, if there are more 1s coming, you remain in state D, this edge, you remain in state D and the output continues to be 1. But whenever you find that there is a 0 coming, that means you again have to start from the beginning, you go back to A, right. This is how you capture the specification of the problem in the form of a state transition diagram, where the nodes indicate the states, the edges represent the transitions. Now, the same information you can capture in the form of a truth table kind of a structure. This is called a state table. Well, there is another more concise way of representing this, but I am first showing the simpler one. Let us assume that there is a reset input. So, when the reset input is 1, see here we are talking about present state, next state, the applied input and the output. So, whenever reset is activated, irrespective of what the present state is, the next state will be A. that means you will be going to A and the output is 0. So, when the reset is 0, which is the normal mode of operation, there the inputs are coming one by one. Now, you see this table. So, when you are in A and the input is 0, according to this diagram you remain in A, you remain in A with output 0, 0 slash 0. Well, if you are in A, but the input is 1, that means you are taking this path, no sorry not this, this path. So, the input is 1 and the output is 0 and you go to state B. So, state B with output 0. So, wherein in state B is 0, you come back this one. If B is 1, you go to C, this one. So, in C similarly, if it is 1, you go to D. In D, if it is 0, you go back to A. If D it is 1, you remain in D, right. So, these two are equivalent actually. Okay. So, you can either show it in a diagram form or in a table form. Now, what I have said is that this table can be expressed more concisely or in a more compact way in this form I am showing here. So, the state transition diagram I am showing side by side for convenience, and on the right hand side whatever I am showing, this is the concise state table, more concise form of state table. So, let us see how we have done it. You see there are broadly two columns. The first column specifies the present state of the system PS. It can be A, B, C or D. Well, here and the next part of it specifies two things, next state comma Z, Z is the output, next state is where you are going comma Z is the output value that is being generated. Now, as you can see there are 4 columns in the second part. There is something called R x. What is R x? R represents the reset input, x represents the actual bit that is coming, the actual input. So, whenever R is 1, that means you are resetting. So, you can see the third and fourth columns where R is 1. So, your next state is becoming A because it is reset to A and the output is also 0. So, you are resetting the system here. But when R is 0, depending on the value of x, you are taking a decision. Here x is 0. Okay? So, when x is 0, you see from A, if the input is 0, you remain in A with output 0. You write A comma 0. This is the next state and output. So, if it is 1 here, you go to B. If it is 1, you go to B with output 0. From B, if it is 0, you go to A with output 0. From B, if it is 1, you come to C with output 0. In this way, you go on. From C, you go either to A or to D with output 1. From D again, you either go to A or go to D with output 1. Okay? So, this is a way to express the state table in a concise way. In all our examples subsequently, we shall be using this concise notation of the state table to represent a functional behavior. Okay. Now, let us look into some formal definitions of finite state machines. There are broadly two kinds of finite state machines called Mealy machine and Mood machine. But before coming to the distinction between these two kind of machine, let us try to formally define, mathematically define what a finite state machine is. Well, from a designer's point of view, it is a circuit. It has some memory, some state, inputs are coming, outputs are generated, states are changing. This is intuitively you are specifying, but mathematically when you capture this information, how should you specify? It is specified in this way. Deterministic finite state machine, this is deterministic because whenever you are applying some inputs, the output is deterministically determined, there is no ambiguity. It is mathematically determined as a 5 tuple. sigma, gamma, S, S0, delta and omega. What does these 6 things mean? This is actually a 6 tuple, not a 5 tuple, actually 6 tuple. This sigma means this set of input combinations. Suppose this circuit has 3 input lines, there will be 8 input combinations. So, sigma will denote the set of all possible 8 input combinations. So, sometimes we call it as the input alphabet. What are the possible input combinations that are possible? Okay. Similarly, gamma is the set of output combinations. In the same way, let us say if there are 4 output lines, there can be 16 possible output combinations 2 to the power 4, that is gamma, set of all possible output combinations. Capital S denotes the set of states. Well, it depends, whenever you have drawn the finite state machine, the state transition diagram, you have some idea how many states are. So, S denotes the set of the states. Like in the example that I have given, there are 4 states A, B, C, D. Okay. And small S0, which is a member of S, is the initial state, because you have to mention from which state you have to start. All right. And of course, this is not enough. You also have to specify something called delta, which is the state transition function. That means, it will tell you that if you are in a state Si and if some particular input I comes, which state you will be going to Sj, that is defined by this function delta. And there is another function called omega, this is called the output function. It says that when you are in certain state and some input comes, what should be my output. So, if we specify all these 6 things, your specification of the FSM is complete, right. So, delta can be mathematically expressed like this. Given a state, given an input from the input alphabet, it determines the next state. Mathematically, in the function notation, you specify it like this: present state, in short PS, and the present input, this alphabet, determines the next state NS. Okay. Now, let us distinguish between milli and mode. You see, milli and mode are identical up to delta. It is omega that distinguishes these 2 types. For a milli machine, the output depends on the present state and also on the present inputs. That means, the output gamma depends on S as well as on the input alphabet. But in a mode machine you can say is a subset of a milli machine. In a mode machine, the output depends only on the present state, it does not depend on the input. So, the output is determined only by the present state. There are many systems where the output that is being generated is not determined by what input you are applying, rather than which state you are in. Well, a classic example is a traffic light controller, where there are some states which you are going through, and depending on which state you are in, so either the red or the yellow or the green lights are glown. So, it is not that you are applying some input, depending on that you decide which light to glow, not exactly like that. Okay. So, milli and mode machine are 2 different types of machines. These are the formal definitions. So, pictorially speaking, the mode machine and milli machine can be depicted like this. For a milli machine, the primary inputs are coming like this, Pi is the primary inputs, PS is the present state, NS is the next state. Now, you see, in any circuit realization, there will be a set of flip flops which will be storing the present state. The outputs of the flip flops that will define the PS. Okay. And there will be some combinational circuit here, which will take the primary inputs and also this present state, and it will determine the next state. Well, one thing I have not shown, it is there, it is the clock. The clock is also there. So, whenever the clock comes, the next state will get stored in the flip flop and it will now become the present state. Okay. And there is another combinational circuit called the output logic, which again takes the PI and the present state as input and generates the primary outputs PO. For a Moore machine, the first part is the same, but for output logic it takes only one input, the PS. It does not take PI as the other input. Okay. The output depends only on the present state. This is how you distinguish between these two types of machines. Now, when you talk about a synchronous sequential machine, a synchronous sequential machine is a sequential machine which is synchronized by a clock. So, whenever the clock signal comes, the active clock edges comes, the states keep on changing. The flip flops are triggered by some leading edge or falling edge of the clock, only then some changes will take place. Okay. So, pictorially speaking, so a synchronous sequential machine can be modeled like this. There are n input lines, let us say the input variables are x 1 to x n. There are m output lines, z 1 to z m. There are state variable, let us say there are memory elements or flip flops, these are flip flops. Okay. There are k number of flip flops. So, I am saying that there are k number of state variables which are y 1 to y k, small y 1 to small y k, these are called state variables. Now, according to our definition of FSM, the input alphabet consists of all possible input combinations. Because there are n inputs, there will be 2 to the power n such combinations. Similarly, output alphabet, there are m outputs, all 2 to the power m combinations, and the states, there are k number of state variables. So, there will be 2 to the power k states. So, as this diagram shows, this small y 1 to y k, this is my present state, and the capital Y 1 to Y k, which is fed to the input of the memory elements, this will be my next state. So, the clock is not shown. When the clock comes, the next state will become my present state, right. Copied to the present state. Okay. So, now let me just tell you about the steps that are required when you synthesize a synchronous sequential circuit. The steps are as follows. First, you start with a description of the problem. For any problem, you have to start with the description. You will be forming the state diagram or the state table. This is the first step. This is one way to formally capture the specification of the system. Okay. Then, the second step we shall not be considering now, this will be discussed later, because this table or the diagram may contain some redundant states. That means, you can remove or reduce the number of states in some way. So, we shall learn later how to reduce a given state table or a state transition diagram, or in other ways to minimize it, we shall see it later. So, this is an optional step, we skip this for now for the time being. Then we do something called state assignment. What is state assignment? In the example that I have seen so far, we named the states at A, B, C and D, but ultimately these states will be represented by flip flops. So, the 4 states can be represented in binary, let us say using 0001 1011, that is called state assignment. Each state is assigned a binary code, okay? And also you decide what kind of memory elements you will be choosing, JK, D, T or SR. Okay? and of course, the final circuit complexity will depend on this selection, and we shall see how to do it. From this state assignment and selection of memory elements, you first determine something called transition and output tables, and then the excitation table. And from the excitation table, you use some minimization technique. You start with something called excitation and output functions, minimize them, and finally obtain the circuit diagram. Now, we shall be looking at a number of examples to illustrate this process, so that it becomes quite clear to you, right. But this is the overall steps for any kind of synthesis of synchronous sequential circuits that you are trying to attempt. Okay. So, with this we come to the end of this lecture, where we have talked about something about finite state machines FSMs, the different types of FSMs, and finally, we talked about the steps that are required to synthesize a circuit starting from a FSM specification. In the next few lectures, we shall be looking at some examples and see how this synthesis is actually carried out. Thank you.